So the second example, unlike the first one's considered the easiest type of word problem because in the question they gave you the equation. The next two examples that we're going to do, we're just going to get a situation and we have to take that situation, figure out what's going on, realize that it's periodic in nature, graph it, and get the equation ourselves. So it's a little bit more involved. In this one, we have a Ferris wheel. So if we draw a picture, sometimes it's helpful to have a little picture. If you don't know what a Ferris wheel is, it is a ride that you get to go on. We should draw the spokes, otherwise it doesn't really. There we go. And fancy chairs. And we'll put people on these chairs. Green people. Whee. Big smiles on their faces. This guy's going to get in trouble. There we go. So we got people going around this Ferris wheel. This Ferris wheel rotates once every 20 seconds and has a radius of 15 meters. Ooh, we could make this question really interesting if we changed some of the units. So we could make it 15-kilometer radius, the biggest Ferris wheel in the world, and change it to rotate every 20 milliseconds. If you imagine how fast you would be traveling around a 15-kilometer radius Ferris wheel in 20 milliseconds. Anyways, then that guy who's hanging there would get thrown very, very far. Wow, that's not what I was going to do, but I did that. I wanted to, wow. I want to just highlight this and make it a little bit smaller. Oh, there we go. That's perfect. Okay. So what we need to do is take this situation. Here's the ground level right here. So where the ground level is, does it make sense to graph height along your y-axis and time along your x-axis? And so we've got our Ferris wheel off to the side there so we can kind of visualize what's happening as we go. Now, when we read this question, back to the beginning, we have a passenger starting at the bottom of the Ferris wheel. So here's our token passenger. There we go, starting right there. Super happy to be going on the Ferris wheel. Starting at 1 meter. So how do we show that on our graph? That's going to be a point. It's going to be the lowest point at 1 meter. And can you see that that would be, well, I guess I don't need, I'll put the units under here and just label this as 1. Does that make sense that that's where you would start? At time 0, you're starting at the bottom. It's very hard to start on a Ferris wheel at the top. I don't think there's any places where they allow that. So we know that point. How do we use the rest of the information in this question to draw the other points? Now, because this is going around in a circle, it repeats itself. And anything that goes around in a circle and repeats itself will draw a sinusoidal graph. So it'll draw a sine or a cosine graph. So what's another point that we could graph on here? I've got 0, 1. Tell me another time that I could put on. 5 seconds I could put on? Someone said 20 seconds. Where will you be at 20 seconds? Back at the base, back at the beginning. Okay? So that sort of represents one full time around. That will be 1 period. Where will you be at 10 seconds? Right? 10 seconds, you'll be halfway. Woohoo! That's the exciting part. As a kid, I don't know if you've ever been on a Ferris wheel, but as a kid, it was always exciting when it stopped and you were right at the top. You hated that? That was too scary? So at 20, oh, will it be at, no, it won't be at 20. How high will you be?
It'll be at 31.
Here, it'll be, how do we know it's going to be at 31?
Because the radius is 15, which means the diameter 30.
So
And
this,
the 1 meter off.
yes, so the radius is 15, so that means this is 15 to the center, and there'll be another 15 up to the top. So at 10 seconds, you're going to be 31 meters above the ground. What's our center line going to be then? That center line would be at 16, because that has to match up with the center of our Ferris wheel, and if our radius is 15, then that you'd go from your minimum up 15 to the middle and up 15 again. And at 5 seconds, does it make sense that at 5, if 10 seconds you're up here, at 0 you're down here, 5 seconds you'd be here, 10 here, 15 there, and just keep going around and around. Whoa! Okay. Yeah, but always wear a seatbelt on a Ferris wheel. So we get our main points, and once we have that, we can draw our sinusoidal curve through those points. Now we need to find an equation for this. This question doesn't specify which equation, so you have a choice. In fact, what we're going to do is we're going to do one in sine and one in cosine, even though we've learned from our last examples that you can get from a graph an infinite amount of right answers for this curve with sine and cosine. What changes is the starting point. But the DAB part, the D, the A, and the B, they're going to stay the same no matter if it's a sine graph or a cosine graph. So just off to the side here, let's think about the D, the A, and the B. Can you tell me what my D value is going to be? 16, because that D is that's our center line, our sinusoidal axis, our average. So it's going to be 16. Our A stands for our amplitude. It's going to be 15. In this case, it's the same as the radius of our Ferris wheel. Now our B value, we had formulas that said, remember our B value helps us find our period. Our period is always 2 pi over our B value. And if we rearrange this, we can say our B value is always 2 pi over our period, because your B value causes things to be stretched or compressed. In this one, can you see that our period is 20? And so our B value will be 2 pi over 20. And I actually like to not reduce that, because if it's in this form, because you know that your period is 2 pi over your B value, or your B value is 2 pi over your period, in this form it's really easy to see that your period is 20. If we reduce it to pi over 10, it's not in that form, and then you'd have to do some mathematics to figure out what your period would be. So you'll often see questions leave it as 2 pi over something so that you can see the period in the equation. So once we have those three things, we can start writing two equations, one with sine, one with cosine. So if my 15, my A value is going to be the same for both of them. One with sine, one with cosine. My B value is going to be the same for both of them. I'm going to leave space for my C value because that's what can change. And my D value is also going to stay the same for both of them. So the last thing we need to do when finding an equation is think about our C value. Now, your C value from transformations, that's what moves things left and right. You've started to see some of the language in this unit. Sometimes they talk about that being a phase shift. I like to think of it as a starting point. So when we think about a normal sine graph, where does it start? Starts in the middle going up. So now we need to find that starting point on our graph. Do we have a point that's in the middle going up?
5.
Yes, right here at 5. In the middle, going up. So since I have that point in the middle going up, and it starts at 5, which has moved 5 to the right, that's telling me my phase shift. This graph would have been moved 5 to the right to get that. So we go and add that in for our sine graph, minus 5. Where does a cosine graph start? Starts at a maximum, right? Right at the top. So do we have that point anywhere on here? Yes. There's a point right at the top. That happens 10 to the right. So we could put that in as minus 10. Yes?
Would it be right in the exam if we simply put minus cosine?
Yes, and I was going to just say that probably the most common equation that someone would make using this one is, see how the graph starts at a minimum? If I wrote a negative cosgraph, so the 15 stays the same, the 2 pi over 20 stays the same, the plus 16 stays the same, but if I make it a negative out front, a negative cosgraph starts at a minimum. And if I start at a minimum, can you see that there's no shift needed? Because that's right here already at 0. So you could just write x in there, and you would have no phase shift for that graph. And that would be a third equation that would be right. Now, if you're given the choice of sine or cosine in any equation that you would like, I usually find I like writing the cosine ones better, because it's much easier to see maximums and minimums than it is to find the middle line sometimes. And in particular in this one, we're starting at a minimum, so that really makes sense to do a negative cosgraph. So what I want you to do is I want you to get this picture on your graphing calculator. If you don't have a graphing calculator, I have a couple extras here. And once you've chosen that equation, you also have to go to your window and set up your window so it matches the window that we see here. So the window that I chose is on my x. I went from -3 so I could see my y-axis. And since we went up to 20, I went a little bit further to 25 just to see a little bit extra. Same thing with our y values. I started with a negative so I could see my x-axis. And since we went up to 31, I went a little bit higher to 35. Then when we hit graph, we can see our picture. And it's going very fast. Now in part B, it said estimate the height after 22 seconds. So what we're going to do with this one, when it says estimate, you can basically put any reasonable answer down within a given amount of error and you will get it right. So in this case, what they're looking for is, can you look at this graph and say at 22 seconds, which is right here, what height would you estimate that at? So if we estimated that at 22 seconds, you just go across here, and what value do you think that's close to? 4, 5, okay? 4 meters. So that is our estimate, and that would be fine. As long as you're not picking an answer that is like 16 and above, which wouldn't make sense, you know where that range is, you have a little bit of leeway. Now if we wanted to use our graphing calculator to figure out what is that exactly, all of our options for our graphing calculator are above this trace button with calculate. So if we go second and trace, this menu comes up. We've already done a few of these things, but the first one with value, if you push value, it lets you type in anything for x. So if I want to find out exactly what it is at 22 to see how close our estimate is, I can type in 22, push enter, and it's 3.86. So we were pretty good. Our estimate of 4, when in reality it's 3.86, is really, really close. If you want to estimate when you're going to be 20 meters above the ground, there's nothing on that menu that lets you plug in a y value. So I can plug in x values, but when I go to the second calculate menu, it lets me find x-intercepts, it lets me find minimums and maximums where graphs intersect, but it doesn't let me plug in a y value. So what I do is I'll go to y equals, I'll go to the second one, I'll type in 20, and that'll draw a horizontal line where the y value is 20. Yes?
Wouldn't you do the inverse of the function?
Yes, you could do the inverse of the function and type that in. The problem with the inverse of a sinusoidal is it doesn't pass the horizontal line test, so then the inverse doesn't pass the vertical line test, and there's not actually a function you could type in for all of it. Because here, you can see it's going to hit 2 points. But if you did the inverse, a function can only hit 1 point, and so that would be a problem. So there's 2 different points where it hits 20. Again, this says estimate, so estimate means you could have gone to your graph, draw on the line where y equals 20, estimate where that is, go across, and do this point, and go down and maybe say, it looks like it's at 7 and 13. Does that seem reasonable? Right down here to 7. And 1 at 13. If we want to find it exactly, what we can do is find out where these graphs intersect. So on our graphing calculator, again, now we can go second calculate. Number 5 says where things intersect. If you push enter 3 times, it goes from first curve to second curve. It always gets you to guess. I think it's going to be over here. Oh, I was off. And it finds it for you. So we found out the first one is 14.14. This one right here. 14.14. How can I figure this one out without using my calculator? So how do I know it's 5.86?
Because it's a different, from 10 to that point was 4.14.
So you're saying from 10, which is here, this way is 4.14. Oh, that's fancy. I don't know. It was accidental.
I'll do it again.
Okay. And then this side would also have to be 4.14. And so if I took 10 and subtracted 4.14, I get 5.86. It is symmetrical, so we could figure it out that way. Of course, we can go back to our graphing calculator and calculate that intersection as well. Now, the cursor is closer to that one. Your calculator will always find the intersection that it's closest to. So now I'm close enough now, but it's sometimes fun just to hit it 3 times, and sure enough, 5.86 is our second answer. So we can estimate it by using the graph that we've drawn. We can use our graphing calculator to find things out exactly. Our last example from this page is with tides. Tides are also periodic. They come in, they go out. They come in, they go out. And if they follow a time frame like that, then they can be modeled by a sine and a cosine graph. This is a little bit tricky. Again, once you get out of high school, where most of your word problems are contrived so that the numbers aren't too bad, when you get into real life examples where you want to model things, the numbers don't always turn out nicely. And so we have to deal with that data as well. For example, time isn't really nice for graphing. Because how do you graph 430? Do you do 4.3? 4.5. That seems to make sense, right? Because it's half an hour. So 4.5 makes sense for 430. What about 1042? Ugh. Right? So using real life data, sometimes you've got to work with that and figure out how am I going to use this well. So when we go to start graphing this, I like that we've got 4.5. So if I draw my axes, if I measure, I'm going to say 4.5 is right here. We have that point. At 430, it is 8 meters. So I'm going to put 8 up here and draw that point. How am I going to mark 1042? 6 hours and 12 minutes later. So how do we figure out what decimal 42 minutes should be? So you say it should be 0.7. So that is correct. It's going to be 10.7. So why is 1042 equal to 10.7? How did you figure out that 42 is 7, right? That's, again, if you just took that part of my video and you're like, what? Your teacher was telling you 42 was 7?
Because 42 is 7/10 of 60 minutes.
Okay, so what we're doing is we're finding out what fraction of 60 is 42 minutes. Because 1 whole, in this case, is an hour, which is 60 minutes. And 42 out of 60, if you do that in your calculator, you get 0.7. If you do this without your calculator, can you see that you can divide both of them by 6? And then you get 7/10, and that might be something you know directly is 0.7 without your calculator. So we have 10.7, and at 10.7, the depth is 2 meters. And this is all you need for a sinusoidal graph. If you have one maximum and the following minimum, or one minimum and the following maximum, it's enough information for the entire graph. So what are things that we need to find the equation? We need our center line. Can you see that your center line should be right here in the middle somewhere? What's its value? What's right between 8 and 2? 3 is not right between 8 and 2. 5. I know what you're doing. So how do we find that 5? Well, sometimes you can just eyeball it and figure it out. But it is that center line we call an average. So if you think, what's the average of 8 and 2? Right? First quiz in this unit, you got 2%. Second quiz, you studied a lot more, you got 8%. So your average in this unit so far is 5%. Well, that's not really a good example. But how do you find an average? Add the 2 up. 8 plus 2 is 10. Divide by 2, you get 5. So that center line is always an average. Now, with that center line, you've got your d value. So let's just mark what we know so far. We've got our d value. We know that it's 5. We've got our amplitude now, because that's from the center line to the top. That's where that 3 comes into play. But to figure out our b value is going to be 2 pi over our period. We need to know what our period is. How do those 2 points tell us our period? So we know between these two, how far is this? How many hours? 6.2 hours. Okay. 6.2 hours from that point to that point. And it would do the same thing, right? It would double because of how it's symmetrical. I mean, right now we could sort of start drawing things up of what it's going to look like. And if it's 6.2 from there to there, to get to this next point, you'd have to go another 6.2. And so our total period is 12.4, and our b value is 2 pi over our period. So our b value will be 2 pi over 12.4. Now this question again asked us to write one equation with sine and one equation with cosine. And so we can start that now because the d, the a, and the b stay the same whether you're using sine or cosine. So I'm going to start writing y equals for both of them. Your amplitude is 3 for both your sine graph and your cos graph. Your period is 2 pi over 12.4. That would stay, oops. That would stay the same for both of them. Leave some space for our phase shift, and our center line is plus 5 for both of them. So again, the d, the a, and the b, they stay the same no matter which graph you're using. Now, the only changes you can make now is to decide where my phase shift is, and sometimes you might add a negative in front of your a value if you wanted to start at a minimum instead of a maximum. So where does a sine graph start? Well, let's do the cos graph first because it's easier.
Would it be easier for the cos graph just to make it a negative and say the translation is 10.7?
Well, but then you're going farther. Wouldn't it be easier just to start with your maximum? So where does a cos graph start? Cos graph starts at a maximum. Where's our first maximum? That's right here, shifted 4.5 to the right. So we could have that show up in our equation by going x minus 4.5. In our sine graph, this is where I say often your sine graph is harder to make, because in these kind of questions they give you one maximum and one minimum. So you have a max or a min, easy to use a cos graph. You have to do a little bit of work to figure out your sine graph. So where does the sine graph start? In the middle going up. Can you see on this graph, I actually, like if I extend this, I have two places where that can happen. It can happen here in the middle going up, or it could happen here in the middle going up. We need to figure out what one of those values are.
So it's 2.5.
Not necessarily. So I see what you did here. You cut this in half, but that's not necessarily the case because it might have been shifted more. It's not perfectly half of 4.5. What we need to figure out is what are these marks in between, right? If I added the 4 sections, because normally you take a period and divide it into 4 sections, there would be, this is the spacing that would be needed to go from one section to the next. So there would be another one there. And actually the next one would be there, so that's why dividing between 0 and 4.5 in half wouldn't work. How much is it in between one of these spaces? 3.1. How did you figure out that? So you knew that this was 6.2, and if you cut that in half, one of those sections would be 3.1. So if I went back 3.1 from 4.5, I would end at 1.4. Or if I went up 3.1 from 10.7, I would get to 13.8. So when I go to write, what is going to be the value that I shift? I could use either one of those, so I can go x minus, I'll use the 1.4, but you could also go x minus 13.8. Both of those will work. And then from here it says, once we've got both equations, it's asking us to estimate again. Estimate at 130. This time we won't put it into our graphing calculator. We'll just do the estimate. But where would 130 be on this? Right? This is our depth. We should probably label our axes here. This is time. Where's 130 on here?
It would be
13.5. Because it's 1 hour after 12. So that goes to 13. And 130 is half of an hour, so 13.5. If you went up from here and estimated that, it should be somewhere between 2 and 5. So pick a number, approximately 3.5 meters. There's our estimate. If we want to find out what it is exactly, then we're going to have to use our graphing calculator to plug that in, get that graph.
Just insert that value, 13.5.
You could also just insert that value into x, and then you wouldn't need to graph it. So what Peter's saying there is, since I know that the x value is going to be 13.5, I could type in either one of these two equations with an x value at 13.5 and figure out what it would be. Now, all of these equations are using original period of 2 pi, so we need to make sure that our calculator is in radians, because all of the equations that we've done so far have been working in radians. So what we're going to do for the last 20 minutes is there's 2 examples on this sheet for you to try that are similar to the ones that we've done. And if you are done those ones, out of your workbook in section 6.7, there's an additional word problems you can do if you're looking for more, questions 3 to 9. The homework assignment listed at the bottom of your page, you can ignore that because that's a different handout. So you can ignore the homework at the bottom of the page if you want to write questions 3 through 9 on there.